Hey, this is James Diamond with GlockCNC, and now that I have a moment because I have to wait on some things to cool down, I decided I'd go ahead and make a couple videos, as well as I got to get into some emails, running behind them emails, kind of thing like that. Always a lot going on. Anyway, this particular video I'm going to make is some people had some questions about how do I measure runout, on my headstocks, and the other is grinding. They'd like to know a little more information about the grinding steps and what we've kind of learned from the grinding. And some guys, they're interested in doing some ID/OD grinding themselves and want to know, what should I expect? So I'll give you basically our take on what we found out. And then there has been some stuff that we just didn't know when we got started, and after we got started into our let's say the bigger headstocks like this, we had to actually switch the type of grinding at one point that we did because of cost. Things changed. COVID came along, and the shops that would kind of do almost like a favor for you, before. They now have to kind of change their policies, and what was reasonable before now is outrageously priced. So anyway, let's get into it. Let's talk about measuring runout. Now, measuring runout is actually kind of a weird thing. It's not necessarily as simple as, okay, I'm going to put a dial test indicator on here and rotate my spindle and see what kind of runout. Sometimes it's going to be accurate, sometimes it's not going to be accurate, and here's why. And when you're talking about measuring, if you've got a tolerance in the thousands, yeah, you can get the readout from it. You can get the readout from it. But if you're talking into, let's say, the 10,000ths range, it's much more difficult to actually genuinely get a read of what your net runout is on the spindle. This is why that it is kind of a challenge to do, and I'll tell you the only way that can really be done. It's a challenge because when you're talking about 10,000ths or millionths, you're talking about surface roughness being able to affect the readout on your indicator, or you might have what's called a negative or a positive imperfection. Okay, so instead of the surface on here, let's say, being perfectly conical round, maybe there's a dip in there, or maybe there's a raise in there at some point. Now, the dips, depending on the size of it and its shape, may have really no net effect. More often than not, though, a positive or raised portion of it would have an effect, and you probably would know that if you ever got a chip caught in there, that it can affect things, and also you can actually ruin your surface in there by vibration. But at any rate, the reason it may not necessarily, I should have grabbed a tool holder. I don't have one sitting around me. Little BT30 tool holder. The reason it doesn't always, if you get an imperfection in there, doesn't actually affect the net output for your runout, is because sometimes that tool, those are nice, hardened cones that you're sticking in there. Sometimes whatever that imperfection is gets bridged, and it doesn't really come into play. And depending on where the imperfection is at on the taper, it actually also makes a difference. So really, to get the best reading of what your accuracy is in here as far as runout, the whole thing, the whole cone on the inside almost has to be taken into consideration. Now, if there's a major thing, if there's something that the indicator is really going nuts over, then then there's probably a problem. But you can rotate one of these. I've seen guys rotate it and think, oh, this thing is out of whack. But by the time they got their tooling in there, it's like, okay, I'm getting just as good as this as one that measured differently. What gives? It's because the whole thing, how it connects to each other. When it comes to you've got to have what's called a test bar, and they make them for each size. They have them for BT30, they have them for Cat 40, they have them for BT, all the BTs, Cats, and they have them for HSKs. And what the advantage of that is that when you mount it inside your spindle, okay, it now takes in consideration, you could say, all of the different surface things or anomalies that maybe your indicator detected that may or may not make a difference on what the net runout is to you. So that sticks in there, it pulls in there with a pull bar, and then a certain portion of a straight shank comes out here and sets. And you have to get a quality one, and I'll tell you why. So what happens is you'll put your indicator out at the farthest most point, and as you rotate this, now you can start to get an idea of what its net accuracy is, and that will give it to you combined with, okay, what the bearings accuracy is going to be, what, the accuracy of this taper is going to be, all interacting together. That's the way to do it. Now, the test bars, you've got to be really careful even on which test bar you get, because if you decide, oh, look, I found a test bar I can get out of Asia, pretty cheap. Well, they're really going to have no way of knowing what you've genuinely got until you send that off to get it certified. And the other portion is you sometimes don't know the quality or what the hardness of it is, or if it's got some deformation, when you pull that thing tight. The best way is to get a certified test bar, either out of Europe or stateside. And they're not cheap, unfortunately. For the average guy, it's not real practical, because you could probably pick up a used one for between $500 and $1,000, but you're gonna have to get it recertified. New ones, man, they can be in the thousands pretty easily. So it's kind of an expensive thing that might ultimately end up being academic for you, but that's the only way to genuinely measure it. And if you're putting an indicator on there, it can give you an idea of the runout, but it's not really what you need to know. Unfortunately, there's no easy way other than spending the money on that thing. But again, if it's a big imperfection, it's a problem. So now you know how you can measure it. So if you're making something that's conical and it rotates, now you know how to. You'd have to get a custom ground something or other to put in there, and that'll be really expensive. Or you just want to measure, the taper on your machine. Okay, so let's talk about, I'm going to take a drink here. Let's talk about grinding, and some of you guys, you said you wanted to do some grinding. There's different types of grinding, of course. A gazillion types, just OD, ID, which is what we're going to talk about because that's where experience is. But there's also surface grinders. There are rotary surface grinders. There are, double disc grinders. There's centerless grinders. So lots of grinders. We'll talk about just IDOD. Now, and I'll tell you how it can get complex on you, okay? So on the screen, if you're looking on here, this bottom piece, which is also represented by this top piece right here. This bottom piece is just straight across. And the inside of this, let's say, is just, parallel and straight sweep across. For that kind of thing, very easy, typically, for a grinding shop to do. Very easy. In fact, what they can do is I just said I wouldn't talk about different grinding strategies, but here's one. So let's say this bar, maybe they'll take that bar and they'll put it in a centerless grinder to get the thing really round. And now that it's really round, now maybe they'll clamp it into whatever machine is going to cut, its final shape. And then they know, because let's say this is it. This thing is really round because it was, ground ahead of time on the surface before they cut any other features, that when they put this, in maybe for a final grinding of maybe an inside feature or a face or something, they know that it's really easy. They know that it doesn't take much work to indicate this in to do the grind. But what gets more complex is, okay, you've got this flat surface area, but now you've got flat surface area and you got a conical part on the inside that has to be dealt with. Okay, so now it adds a little bit of new complexity. But even again, see, all of our headstocks, the spindles we used in them prior to introducing the new variety, they were all just straight shanked, which was very easy for grinding, and we never really had to think about it. We just told them this is the accuracy we need, and the machine shop would cut the piece and then they'd go off to the grinders and just be done. But that we had a bit of an educational curve when it came to making something a little more complex like this. It's because there's steps in here. And this is what we didn't know, and I'll give you a little bit of history, how we even came to this, is some of you I know this, the first couple batches of these, and this is one of the defective ones we got out of China. They messed them up a couple times, and we've had to have spindles remade so many times. It is like embarrassing to even tell anybody how many times these were redone, in whole or in part, before we actually finally got down to how these had to be done, and ultimately ended up having to change the manufacturing strategy to get what we need. Okay, so the area that gets complex that we didn't realize is each spot that there's a bearing. Now, if you look on the screen over here, you have to forgive me if my eyes are going all over the place. I have multiple screens and I might be looking at it. So if you look at the screen down here, or maybe it's going to end up being down here, you'll see this is, let's say, an example of a spindle arbor that's got multiple steps in it. And this is going to represent where the bearings sit on the spindle once it's installed. Now, these areas, okay, are going to be critical for your grinder. What they have to do is they have to put a test indicator here, 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 and here. So each of the area where the bearing race is, it'd be the bearing sits here, a bearing sits here, and a bearing sits here. So they will figure out what the runout is on each of those, okay? And then they have to average it. So they'll average it, so then they'll know, okay, how much runout will this thing ultimately look like, because we know it's not going to be perfect, because you're not going to actually produce anything literally perfect, or it's not going to be, 2 millionths or something like that. So they know what this has to look like as far as, okay, now we got the average, so that we know that when we come in here and sweep the inside of this taper, that it's going to be, as a whole, it's going to be accurate. Because you can't just do this surface right here, or just this area, and then think, okay, we'll just chuck this area, since we know the runout here, we'll chuck this, and then you come in and do the sweep. Can't be done, because let's say this, if you look on the screen again, this area right down here, this bearing that sits over here in the back, if it's not right, and the runout is different enough so from this, it's still going to be doing this kind of thing. So it has to be right all the way across. It gets a little more complex because, these all have to be, they all have to be dialed in, so to speak, manually. When they're setting these up, it's time consuming for the grinding shop to actually do these. And I thought they were just putting these in machines and going, basically. I knew they had to do some setup, but not as much. In fact, the grinding shop that we ultimately landed on that did it wouldn't even allow us actually to photograph the setup or show it being done, because apparently their strategy is kind of their bread and butter and trade secret. So anyway, the different areas here, different steps, can make it a little more complex, and the longer the part, it could also be more complex too. That when this shape is being cut on a lathe, you're going to have actually a different runout here, and here and here. There's going to be different runout all during the whole thing, because the lathe is not going to, do something again. It's not going to cut something into 2 millionths of accuracy. And the farther out, that it is from where it's chucked, maybe it's going to change the runout because deflection, or the materials, or it could even be thermally. Things might, somebody opens a shop door, and you got the case open on the machine somehow with the safety disabled or whatever, or not even that, it just sucks in and blows in some cold air. It can change this. So what you had when you started out here might not be the same by the time it got down to here. So this area where these bearing races set ended up being critically important. We knew it was important, but they ended up being more critical than we thought. Because if this has very much runout in either of them, or the combination of them, the combined average runout is very high, then you can't get a good grind. And you can't go back and regrind these surfaces, because then it'll be out of spec for sitting in the bearings. And I'll tell you how we discovered this. We discovered this because when we finally got a machine shop that would do us right here, and we got all these cut, and then we sent them all off to get ground, we knew that we got a box of them back of each size of spindle. It's like, these are unusable because they're going to be too far out. But as we got to assembling some of these, we noticed that there is definitely a portion of them that by the time everything was all assembled and put together, the runout wasn't where it should be. It was maybe anywhere from, let's say, 7/10,000ths, 8 to 9/10,000ths, and some of them even over 1,000ths. And we had to go back to the grinding shop and say, hey, what are we doing wrong? What's, kind of what gives? And that's when we found out they indicate these in different spots, and then they have to set this in there. These get all set in manually, and that meant we had to change our strategy as far as how this is manufacturing. And something for you to consider too, if you're going to get something ground, especially if you're either that's going to be conical or something that's kind of an odd shape, or you got steps in it, talk to the grinding shop first, and kind of, if sometimes they don't always think like a machinist, though. It's kind of weird. I don't know what it is. Sometimes they can give you some input. Sometimes they don't. When they don't, then it ends up being trial and error and money. But changing the strategy on this, we ended up having to either make a choice of continue to have these, all turned on the lathes and then send them out like we did, to the grinding shop, and just know that a certain portion of them aren't going to be any good. And we didn't want to do that, and it was kind of a problem for us because while we had plenty of them that were good, we had some really big orders for parts from big institutions or government, and those orders were made before even we released things to the public, so they got filled, and then we had kind of like a handful of things left over, that we could send out, to our other customers, because we knew that we couldn't send them out, with them out of round, So, but we figured that all out and got them, got everything all set up. So what we ended up doing is, when these come from the shop, cut as a lathe, there's a little extra material on these different surfaces, and then we have like the bearing surfaces ground to where they need to be, and then that means we can get this surface and this face ground to where we need to be, and that, in a nutshell, is what we didn't even realize ahead of time. Now, there's going to be some things as you go into, if you're introducing a new product, there's always going to be something that you just don't know until you move forward, and you have to make the best decision you can with the information you have and move forward. Otherwise, nothing ever gets done and nothing gets to market. And what I've also learned too, I know it's a little extra, but what I've also learned is each time you have something. Let's say on the screen here, you have this CAD drawing that you made and it gets deleted somehow, or something corrupts it, and you don't have access to it, or whatever it is, or or what on the surface, like these mini disasters, like, oh my goodness, COVID hit and this is all delayed, and oh my goodness, they made these things incorrect when over in Asia, and we know they're not going to give you your money back, and each time you have something like this happen. It's terrible. It is terrible, and it's a growing pain, and it can be a pain for you. It can be a pain for your customer base, but ultimately, it's weird because like on the drawing down here, I've had drawings, and it's my own fault, and sometimes it's not my fault that the thing gets altered or changed, or something happens that I got to start all over again. But the weird thing is when you start all over again on things, it's like the next rendition that you make is a whole lot better than what you had made that you lost, and it's like, okay, so now this is the way this actually should be. So while it's kind of maddening, and you want to kick the couch kind of thing once in a while, and something happens, file gets deleted. It oftentimes it turns out decent. And the weird thing I've discovered is when you're moving forward and you're making parts, and we use a lot of 3D printers. I'll make a video on 3D printing stuff for prototypes. We use a lot of 3D printers, and you start making parts. A lot of what you make is actually junk before you get to where you really need to be for a part. But you want to take mental notes, if not physical notes, of the things that kind of quote-unquote go wrong, because sometimes your best ideas come from whatever those disasters are. And for us, the finished product on this, once we figured everything out, ended up being far better than what was originally done. And one thing, I'm going to throw this in here too. Yes, we did have another manufacturing style that, or strategy, that we bounded these in the bearings and everything, and then had them ground in here by a spindle repair shop. Well, we can no longer do that because the shop we were using, they were actually just kind of doing us a favor. And after COVID started, they are like, okay, we're changing a process. We really need to have it at such and such a price in line with our other customers. And then these went to like $1,000 or $1,200 each to do, which was just, totally unrealistic. So we couldn't grind it that way anymore. So in case you recall me talking about it at some point. Any rate, yeah, each time you've got an iteration, something that needs to change because you've had some something's happened. It is a pain, but the biggest pain I would say for that is probably the amount of time it eats up. Because if you need to make a change that in such a way that, okay, so I can't really use this, you're kind of in the back of the line again when it comes to the shops that you're working with, because they may have had a gazillion orders come in, or they might have a big customer that comes in that's going to take priority, pushes you back, or it's also happened a few times too that you'll have the shop you're working with might have an emergency order come in that they've just got to take, maybe because it's a customer that they had prior, or the money is so good at it they kind of got to take it, and it'll push you back. So each iteration, that's the biggest frustration when it comes to, I think, you making a product and putting it out. If you don't own the machines, or because the machines maybe are just so astronomically costly, and you won't be running them enough to make sense, or put an employee in front of it. So anyway, it's the time in between each iteration, because if you're doing a small order of a $50,000, $100,000 order on something, in that's small potatoes for the shop, let's say, you could be pushed off and pushed off and pushed off. So the way kind of around that ultimately is, as you get everything figured out, then you kind of have a supply, and it becomes just a whole lot easier, moving forward. So I know that was more history than you probably wanted to know in this particular video, but that's what we kind of learned. If you're going into grinding and it's something that's going to be new to you, that you might have to do different iterations. And also know that grinding is expensive, and they may not always know what something is going to cost you until they have done it a few times. It's just that could make or break whether the product makes sense to you, whatever you're doing. Okay, there you go. I made this long enough. At any rate, I've got to get back to doing some things here. I appreciate you taking the time to listen to this. And again, this is James Diamond with GlockCNC. And, I really appreciate all my customers. You guys are great. I've got the greatest customers in the world. So thank you, and I will see you later.